Hello and welcome. Today we're going to be talking about the Cauchy integral formula. And to start this off, we're going to kind of come out of right field here for a bit and go back to something we know about analytic functions. So recall that f of z, if we make it an analytic function, which means that f prime exists on some open domain. Okay, then it implies then that f, if we think of f of z now as equal to u plus iv, it means that both u and v are harmonic. And harmonic means that uxx, that both u and v satisfy the, u, y is equal to 0. Both u and v both satisfy, they both satisfy the Laplace's equation. So vxx plus vyy equals 0 as well. Okay, and of course the harmonic functions as we understand them have three properties. And these are properties that aren't involving anything in dealing with complex variables, but are simply solving a certain PDE. So again, they solve the PDE this. And this is whatever I talk about here, I'm talking about it, I'll use U, but we could be replacing that with V. But the first property is zero net flux. And that's simply stating that if I have a contour in the domain C, in the domain where the function is harmonic, that's somewhere in the plane, right? Then if I look at u, which is the, we'll think of harmonic functions now. This is going to be our velocity field of the fluid, or it could be the electric field if we're talking about potentials. Okay, depending on which physical paradigm you want to deal with. Then we have a zero net flux property, where if I put out of every point on this contour, I create a normal vector, n, and so on and so forth. Has this nice property that if I take if I look at the net flux of this vector field across our contour C, our closed contour, multiplied by, of course, the little tiny ds length segment that we're partitioning our contour into, that's always going to be 0. And that's basically saying that in terms of a velocity field, whatever fluid is flowing in, the same amount of fluid is flowing out, which is a statement of incompressibility of the fluid. Okay. And the second property is that of the maximum property. Okay, and that states that if I have some contour, C, in the plane, where the function is harmonic, i.e. where f of z is analytic, then we know that, that the maximum of u on C and points interior occurs on C. Okay, and that means to say that any points inside of the contour, the function itself does not take on its maximum in there. It can only take on the maximum on the boundary. With the one exception that if f, or if u itself is a constant, in which case then, of course, it takes on the maximum everywhere. Okay, then finally, one of the most important one is that of the mean value property. And that means if I have, again, if I now have if C now, our contour is a circle with a radius, we'll call it capital R, greater than 0. then, and it's going to be centered at z naught, okay? And that means, oops, I should write that, centered at z naught. I'm not talking about f yet here. And then we have this property here. U at z naught can be computed as an average 1 over 2 pi r integral over r over this contour, this circle of radius r. I can put a little CR there if you want, of u of z ds. Now when I mean ds, this is we're talking about a circle here, centered at z naught, and ds is a tiny radial length. So it's, sorry, I should say, yeah, a radial length. Okay, sorry about that poor spelling there. So it's a radial length. So it's not a dz here. This is just a little length segment. Of course, what we're doing is we're averaging the value of this function. This is real value, and we're using this z there as a shorthand because we're talking about a function of. We're now thinking of points in the plane as being complex numbers, but what we're really using that is just that could be an x comma y there. All right, and the idea here is that, and the really important idea that comes out of this is that knowledge about u at z naught can be obtained by examining u at points away from z naught. And that's pretty wild if we think about that. The idea that by looking at, if we average the value of u along that whole circle there, we know what the value of u is in the middle of the circle. And of course, why is this interesting? Now, basically harmonic functions u are very special functions. They're functions where any point is related to surrounding points by this averaging principle. And this is true for any point. I mean, this is any arbitrary point in our domain. And because of that, these harmonic functions are very important and very special. And in general, if I'm thinking about the space of all functions are just an arbitrary mapping of points to points. So, and knowing a value of some random, some typical function in function space, knowing the value, input-output values at a single point tells you nothing about other points because it's completely arbitrary. But for harmonic functions, the relationships between the function value at points distant to another point are related. And it turns out the Cauchy integral formula is going to be intimately related to that fact. So let's now go talk about the Cauchy integral formula. So the Cauchy integral formula. So we're going to state a theorem. And the theorem is fairly straightforward. Say we have a, suppose f is analytic. Okay, that means we're dealing with harmonic functions. Functions where u and v are both analytic, or both harmonic. On some simple closed contour C, okay, and inside of C. Okay, so what we're saying is that there's some contour here, and it could be any shape, and we're going to take this contour in the positive sense now. It's going to be a simple closed contour, and so it's going to be positive. orientation. Okay? And we're saying that everywhere inside of this contour that the function is analytic. Now I'm going to take a point inside. I'll call that z0. Okay, I'm going to take a point inside there. Now I want to know, what I want to know is what is the value of f of z naught? Okay, well it turns out we have a formula called the Cauchy integral formula. Provided it's analytic in this entire region, if I take f of z naught, turns out to be equal to 1 over 2 pi I integral over this contour, and it doesn't have to be a circle, it just has to be a closed contour, it could be misshapen, and then times f of z divided by z minus z naught dz. dz. Alright, so that's a wild formula. Let's see if we can understand this formula a little bit better. So again, this has that similar flavor to that of when we studied harmonic functions, where if we take this integral of the values of f at all these points that are at some distance away from z naught, which is inside, and if we take this integral involving the z minus z naught in the denominator, all of a sudden I can get the value of f at that point. So that's pretty wild. All right, so now let's see if we can get some understanding of this in terms of things maybe we're more familiar with. Okay, so let's talk about that. So what I'm going to actually do is say, well, first of all, this function has this. We can see that f of z minus z naught has a singularity at z naught, right? So even though f is analytic there, because I've divided it by z minus z naught, we have a singularity there. So this integral, the actual integrand of this thing, is not analytic on the domain inside. Okay, so let's see if that. But let's talk about maybe actually doing a. Let's just actually do a contour integral. First of all, though, I can almost put another. We know from the Cauchy-Gorsat theorem, I can put a little boundary around that and have that go in the clockwise direction. And we know that in the intervening region right there, that this integrand is analytic. So I'm going to call that R. So that is analytic on R. Okay? And what we're saying then is we can always deform C into a circle of radius r about z naught. Okay, so let's actually do that then. So now I'm going to parameterize. So z of t then is going to be equal to z naught plus r e to the I t. We're going to take t going from negative pi. Well, actually, let's do 0 all the way to 2 pi. That's easy enough. We're not talking about anything with branch cuts here. We're just going to pick a value of t and go with it. Okay, and clearly what this is going to be a circle, and I make r small enough so that it fits inside my region. I can always do that because we're talking about an open set here. So I can always make r small enough. So there's what we're going to do. And of course, z prime is equal to r I e to the I t. Okay, good. All right. So here we go. And now let's actually just plug it in. So what we can do though is if I see z of t minus z naught, that's then equal to r e to the I t. Okay, so let's put this all together. So I'm going to now look at this integral here. That's going to be 1 over 2 pi I integral from 0 to 2 pi. I've now parameterized this integral. It's going to be f of z of t all divided by r e to the I t, because that's what z minus z naught is, so that's what I get this part here, times I r e to the I t dt. First of all, we see the e to the I t's cancel. We also see that an I cancels there. I'm going to we could cancel these r's, but I actually want to keep them. I'll preserve them. I'll put that 2 pi r out front. That's the one from the denominator, 1 over 2 pi. And now I have an f of what I'm going to call r e to the I t times r dt. Okay, so first of all, because the radius of the circle is such, I can actually call that ds. That now could be my little length segment. Every time we move through an angle, that ds gives me the length segment there. Okay, the second thing is to note that this is actually a function of two harmonic functions, so I can write that 1 over 2 pi r, integral 0 to 2 pi. Sorry, I'm running out of space here. Of u at this at this r e to the I t ds plus 1 over 2 pi r, integral 0 to 2 pi of v. We have to put an I out there, okay? R e to the I t ds. So clearly, this is just invocation of the mean value property for both of these harmonic functions. So we clearly have that this is going to be r at u at z naught plus I at v at z naught. Okay, so that's just the mean value property that we learned from studying partial differential equations. And so that is essentially a proof for this Cauchy integral formula. So what we're really doing is performing an averaging over the real and imaginary parts of this function. Okay, so this obviously is a different way of proving. So in our textbook, we had a very different way of proving that. So I'm going to quickly go through how they prove it, and it's pretty straightforward how they do it. And they basically start with, rather than doing a direct computation like we did, they actually say, well, okay, let's talk about, let's take this this path c, f of z minus z naught dz. Of course, that's our c. It's some, and there are point z naught inside. All right. So first of all, what I'm going to do is I'm going to deform to a circle again. Okay, that's inside, and I'm going to give that a radius rho. Okay. I can always deform, provided I'm analytic in this region. So I am. I'll call that C rho. F of z, z minus z naught, d. Oh, so that should be a dz there. Sorry, dz. Okay. All right. And now I want to prove that 2 pi I, that this is equal to 2 pi I times f of z naught. Okay. So I want to prove that. So what I'm going to do is actually now, let's recall that if I take the integral of C rho of 1 over z minus z naught dz, I can essentially, and remember this z naught, so I can basically translate this whole thing to basically a C rho at 0 of 1 over z dz, and that's going to be 2 pi I. This is the result we've seen time and time again, that the integral of 1 over z is 2 pi I. As long any path around, any closed path around there, including a circle. Okay, and so what we can do then is now I'm going to set this up. So I want to prove that these are equal to each other. So what I'm going to do is now subtract those two things and see if we can determine if it's equal to 0. So here's my C rho of f of z, z minus z naught dz. Okay, that's just this part here. I've rewritten it. Now I want to then go minus f of z naught. Now wherever I see a 2 pi I, I'm going to put this in its place. Okay, and I don't know what this is equal to, but I want to prove that that's equal to 0. But I haven't quite gotten there. I can't write 0 there until I know it's true. And so what I'm going to do then is just do a little bit. We see that if I move this inside, I can turn this into one big integral. F of z minus f of z naught, z minus z naught, dz. Okay, again, I want to prove that this is equal to 0. I'll put a question mark there. I don't know if it's 0 yet. But I do know one thing is that I know that this function is analytic. So I know, so f is analytic, which means that f of z minus f of z naught, all divided by z naught, this goes to f prime of z naught as z goes to z naught. Another consequence is that we know that f is continuous. Any analytic function who has a derivative, it automatically implies that f is continuous, which means that for every epsilon greater than 0, there exists a delta such that when f of z minus f of z naught is less than epsilon, this is true when z minus z naught is less than delta. Okay, so what I'm going to do is take my rho to be now, what we want to do is take rho to be smaller than delta. Okay, and we can always do this. We can always take that rho to be smaller than delta. So delta, of course, is a function of epsilon. So I take an epsilon that's very, very small. That provides a delta. And I can always deform my path, my contour, so that it's small enough to fit inside this. Okay? In which case now, what I want to do then is actually put absolute values on this thing. So I want to do this, C rho. I'm going to put an absolute value there, f of z. Not an absolute value, sorry, a modulus, to be more precise. Put a modulus on that, and then I use that modulus triangle inequality bound. Okay, so first of all, because this is a circle, I know that z minus z naught on this path, when I'm on this path, that's equal to rho. Okay? dz. Okay? And that means that I can write that as follows. And then I know this thing right here is smaller than epsilon. So that means I can do this, c rho. I can call that rho down there. And I know that this is smaller than epsilon, so that means that's actually strictly less than now, dz. And what do I know? I'm taking a path integral, c rho, and so dz then integrates to be the arc length along that whole circle, which is going to be epsilon rho. These are constants with respect to the integral, and that'll be 2 pi times rho, because that's the diameter of the circle. These cancel, and I get 2 pi epsilon. So as epsilon goes to 0, we prove that this whole thing then goes to 0, which then, by definition, means that these two things are equal, which proves the Cauchy integral formula. Okay, so that's nice. We've now got these two ways of doing a proof. One is very direct, and it just uses our knowledge of harmonic functions, and the other one is maybe more complete because it doesn't imply that we know anything about harmonic functions. We just used a direct limit calculation. Okay, so now let's talk about an application. Okay, so let's talk about an application. I'm going to say that I have a g of z. It's this function z all over 9 minus z squared times z plus I. Okay. So if I look at this function, I see clearly that z equals negative I, and z is equal to plus or minus I times 3 are division, or there are points of non-analyticity for this function. So I'm going to draw that on here. So there's minus I. That's one of my singularity points. And then I also have down here minus 3i, and then we have a 3i up there. Okay. Right, I haven't drawn that to scale very well, but you get the idea. So those are points also where we have a singularity of this function. All right, so the next thing we want to do then is say, okay, now we have a contour. The contour is going to be a simple closed contour around z is equal to negative I, but not the plus or minus I times 3. All right, and I'll put this in the positive sense. So I'm going to say this is a positive simple closed contour. So it goes like this. Okay, it's positively oriented. All right, so first of all, then what I can do then is I want to compute this integral, I'll call it I, around this contour of g of z, dz. Okay, well, let's rewrite that then. That's this, right? And I can rewrite it as z over 9 minus z squared times z minus a minus I dz. Okay, so first of all, I can rewrite this yet again as take all the part that is analytic in this range. So the part that's analytic, all of this stuff here, I need to find a function f that's analytic there. I see that 9 minus z squared, z over 9 minus z squared, that function itself is analytic interior and on this contour. And I put in the denominator my z minus a minus I dz. Okay, so I'm going to call this function, I'm going to name a new function. I'll call f of z. It's called z over 9 minus z squared. Okay, so what I know then is that I can use the Cauchy integral formula here to state that this has to be equal to 2 pi I times the value of the function f at negative I. Okay? And that's the Cauchy integral formula used in practice. And that is a way then to compute this integral that wouldn't be otherwise very computable. Okay, so what is the value of f of I? Negative I, sorry. We can plug that in. It's going to be, so I'll put that 2 pi I there as well. So 2 pi I, and then we put z, and that's going to be a negative I up there. So that's this right here. Then minus 9 minus negative I squared. Of course, we have a negative I and an I, and those cancel and make 1. So we have a 2 pi. And then over the bottom, we have a 9 minus negative I squared, and that becomes a negative 1. And minus the minus 1, of course, becomes a positive 1, so we get 10. So then we have pi over 5. Okay, so you see how this works. So if you have a contour that encloses one of your singularities, right there like that, where this is the first power there, if that's a single multiplicity root, and if you're trying to integrate a rational expression like this, where your contour encloses only one of those singularities, then you can sort of essentially break your function off into pieces like that and exploit the Cauchy integral formula in order to compute the integral. Okay, so we'll see how that can play out in practice and why that's a useful piece of knowledge to know. But now we have a way of computing these contour integrals that we otherwise would not be able to compute. All right, so thank you very much.